Yeah, now,
No?
Now it's not muted.
Okay, excellent, thank you. So if I need help, I'll just talk to you to your door.
Yep.
Well, many thanks to those who decided to attend in person, and hello to those who are attending remotely.
Oh!
I hope there are some. What's the name? Kevin, Anas, and Mead told that they will be online, and I anticipate that. Who else?
Queenie.
Queenie maybe will be also through online connection.
Hello, can you guys hear me?
Yes, we can.
We don't see
All right,
you.
thanks.
Okay.
Dimitri, I have a question.
Yes, please.
I've been attending all the CCAS trainings. Do you want me to do a little bit sometime in the future on that?
Yes, and you may want to invite everyone to attend this training next Wednesday.
Well, you had to sign up late.
Yeah,
They probably don't care because not a lot of people are attending now. Okay, thank you. Oh, you're talking about the group meeting. Yeah, that's next week. That's next Wednesday. Yep.
So, who we are and what are we doing? So today's rather complicated meeting with a lot of information. So you've seen that total number of slides for today is like 100.
Oh my.
Some of them are just blank pages to make notes, and some of them are duplications. So, but if you are a little worrying, this little write-up summarizes everything. If you understand each symbol on this printed page, then you do not need this lecture, you can just stand up a little bit. Right? So it will be mostly to illustrate what is there. So who we are and what, before this strange question. Thank you for making definite votes last time. And deciding for Tuesday. I wasn't brave enough to announce it myself, but since you guys voted, it will be, you'll have more time and probably it will be high quality presentations, right? So please send slides by like Monday late evening, like by midnight, because I'm planning to print, distribute, and have everything there, so they will switch quicker, so that we do not waste time. Because if everyone brings presentation on USB, it will take off maybe 2 minutes for each presenter, and then we will be ending too late.
10 o'clock.
Right, which you are not looking forward to. So, we are going to summarize everything we were doing last month, except practical questions, which you will summarize yourself. The hard to focus like in the first chapter we completed interatomic distances, geometry optimization algorithm, and now we nailed down ions and focus on the electronic structure, finding total energy. There are a lot of methods, and probably whoever talks first, I think Anas, but I'll look through the list. We'll overview the list of available methods in Gaussian view, but right now we are focusing on the methodologically the I wouldn't say it is the simplest, I wouldn't say it is most important for practical calculations, but it is academically the solid background for all other methods. So-called Hartree-Fock method. And the goal as an input, we throw in positions of ions in our molecular models, number of electrons, which can differ from feedback. Please switch off the microphone. So we need total energy as an output, and you already know through your practical calculations that there is a molecular orbitals, which are kind of auxiliary things, but they are really helpful in analyzing systems. So we covered several concepts, but we didn't merge them together. So today is a time to pretend. We will not pretend that we are little computers and repeat things as at the end of previous chapter, but we will pretend that we are software engineers, and we will discuss the flow chart. I'm not in the camera. I'm so humble and not anymore. Where's the camera? Great. Good. We will discuss this. Probably it's not seen anyway. Flow chart. Thank you. As if you would be software engineer to rewrite code of, I wouldn't say so ambitious as Gaussian, but minimalistic code for running hard-to-fall calculations and finding total energy out of positions of ions, oxidation state, like spin multiplicity, which protocol will give us total energy. And as by products, molecular orbitals, affinity, ionization energy, right? Energy of orbitals. Number 1. It's just welcome sign. Do we go forward? No? Okay, we do. Very good. So, Roothaan equation, and next time we'll do manual on Gaussian. So here are the subjects. I think we do not have any changes in them. And I just card probably will be moved somewhere to the beginning. So this is the summary of the theory, which will not help on its own. It is only like a password if you enter in the community, or if you're writing a paper and you want people to recognize you as a part of the group. If you are if you would need to squeeze the course in the 3 days, it will be probably the only slide on hard-to-fall theory, right? But looking on the equations probably doesn't tell you much. So we need to make a connection between these abbreviations and what we are doing in computations. And all previous month of efforts and concepts that we did. But you already recognize that there are some orbital energies at the end, and if you were taking linear algebra, you see that it looks like Eigenvalue Problem, right? Everyone in the audience took some level of linear algebra, right? Okay, I'm so happy.
This is my favorite class.
I'm feared. It was my most feared class.
It's usually what most people
I
say.
took it as a freshman, and it was a little too much.
Because most universities have intro linear and more advanced linear. You took advanced linear in your freshman year?
Maybe it was intro, but for me it was overloaded with homeworks, like manual diagonalization of by four matrices and
the identity matrix and doing all the
So this will not help. It is oversimplified, but as a beginning, when starts from coordinates and maybe trial function formulates Fock matrix that shows influence of background charge onto our favorite electron, and then through diagonalization and analysis of convergence, one either repeats the procedure, feeding in new orbitals into formulation of new Fock matrix, or one reports success and gives total energy and other observables. Okay? So if a stranger at Hornbiker store catches you and asks, what is Hartree Fock here? Oh, sure, it is a flow chart with self-consistent reformulation of Fock matrix and diagonalization. Right? I'll try to jump through these slides very quickly. Stop me if you really need something from there, but I don't believe you had enough time to forget. Right? So it is what we did before. So several components, and we are coming to flow chart. Exploiter determinant, mean field, exchange. Exploiter determinant, concept of background charge affecting distribution of each next electron we submit to the system. And there was a concept of an object that is averaged, is an expectation value in respect to all background electrons, but still as an operator in respect to our favorite electron. Right? And this angular bracket stands for Brian cat. Right? So this construction is Fock operator. Kinetic energy of electron, attraction to nucleus, and interaction with background electrons. In this simple example, all background is represented only by electron number 2, but generally it is summation over all available background things. And in some sense, we are doing nothing but solving this equation. But if we think as programmers, it's not enough to formulate and solve, because solution in grid points and spaces is very inefficient. Also, we use variation principle as a criterion of success, when to stop the loop, right? So if the if you deviate from ideal many electron wave function, energy will be bigger. If our deviation from ideal wave function gets smaller and smaller, total energy gets closer and closer to ideal energy, right? Also, what we are going to do today rests on the concept of basis functions, and next week Ben will enlighten us with deeper understanding of what they are. So the one electronic wave functions that are fed into Slater determinants are molecular orbitals, and they are superpositions of atomic orbitals, right? Which are hydrogen-like orbitals or something simpler. And there are two things. First, that as any hydrogen-like orbitals, they have many quantum numbers as indices. And second, that there are several hydrogenic orbitals on each ion. So there is an additional index telling that they are centered not in zero, not in origin, but each set of orbitals is placed at different ions. And this will give additional term into the equations that we will derive by the end of the meeting. If you do have this print out, you see there is a capital S matrix, and it originates. It's overlap matrix. I'll cover it, and it originates from the fact that atoms in a molecule, there is more than one ion in the molecule, and they are situated at different positions. Okay, in the stream of data from input coordinates to total energy, there is only one thing that we can change, is expansion coefficients in front of atomic orbitals that give molecular orbitals, right? Because the rest is like nailed down. We do not have freedom to change it. So in some sense, we are looking for equations for C coefficients. And if you look on this printout, you see it is eigenvalue equation for C vector. C vector is composed of these expansion coefficients. Make sense? Right? Another concept that you have went through is stabilization term in electron-electron interaction. Due to antisymmetry principle and many electron wave functions form a Slater determinant, that upon opening this Bryan-Katz-Slater determinant for Coulombic operator, there will be two types of terms: positive electron-electron repulsion and negative exchange stabilization, right? So those of you who went to PhD defense in physics yesterday saw how true theorists write like hundreds of such diagrams. Some part of our audience was annoyed because on simple question the candidate just started drawing one diagram after another. So electron in electron 1 in state 1 interacts with electron in state 2 at point 2 through Coulombic interaction. And this repels. But if they swap, if our favorite electrons is swapped with one from another one from background, it has negative sign in front and corresponds to stabilization, negative part that makes molecules stable. Yes. And if we take these terms, if you take this operator and perform the partial expectation value, partial average, so we average over background electrons and keep this interaction energy as an operator in respect to our like electron number 1, the diagram will look like scattering from the wall, bouncing back, right? And the equation will include the density of background electrons divided by this delta changing in distances integrated over position of the background electrons. And it will be operator in respect to first electron. The same thing for exchange is also possible, right? And it is done, I'm done with recall, repetition, recital, remembrance, memory about previous lectures, review. I remember this was letter R. Okay. So, first credit is to Douglas. I never knew he's Douglas Hartley, who is, in addition to computational material science, he was involved in building of first computers, which were made of vacuum tubes.
Yeah.
Right? And took much more energy than today's cell phones. And another one, the Hartley didn't use antisymmetry, he used just product. And Vladimir Fock suggested to introduce Slater determinant.
How do you say his middle name?
Alexandrovich? Alexandrovich.
Okay.
Like Alex. Alexandrovich.
Oh, okay.
Yeah. I was taken in the graduate class from one of his graduate students. But I do not think that I inherited much of wisdom, just some connections.
Wow.
So
What's your claim to fame right there?
Huh?
It's your claim to fame right there.
What class?
Covariant and contravariant tensors.
Oh, fun.
He was just gentle and gave grades much higher than anyone deserves. Otherwise, everyone will be killed. So, you already know this concept. So, all but one electrons create background charge, and there is a potential. So, we can tell that Hartree-Fock theory is a mean field theory. So if educated person who is not involved in computation asks you what Hartree-Fock theory is, a stranger, you can tell it is one of the mean field theories. And for many people it will be sufficient answer just to understand what you're doing. Like if it is like hydrodynamic expert, who is not quantum but mathematically advanced, it is the right answer. So the influence of background electrons creates an average mean field of electron-electron interaction that is taken into account to find quantum state of last electron. But a logical connection is that we do not discriminate which electron is first and last. So we find a set of orbitals, and then we populate all electrons into this set of orbitals, and then reformulate background field, and then again solve one electron problem. You see, it's not ideal, but it is a way for approximate account of electron-electron interaction, because anything else will be so much more expensive. This one is not super cheap as well, but it was a breakthrough. And antisymmetry makes molecules stable. If you give it up, everything will explode automatically, or most of molecules. Okay. So, I'm stealing a piece of bread from Ben. So you need to build on the top on what I'm going to tell today. We are not abstract mathematicians. We need to find equations for true molecules. And we need to solve equations, we need to select a basis, because solution on grid points, as those who took introductory and undergraduate quantum theory, they were solving time-dependent Schrödinger equation on grid points. But it is a good educational tool, but it is not practical for big molecules. It's so much more efficient to take a basis, right? Specific basis. And there are two types of bases. So atomic, that like first S function is just decaying exponential near the center of atom, right? And if it is a p orbital, it is multiplied by offset from the center, right? We already covered atomic orbitals, and here is oversimplified representation of them. And there is a plane wave basis that we didn't touch at all, but in the next chapter we will talk about it more and more, because it makes wonders for solid state, for semiconductors. It is not centered on anything. It is just plane waves going across the universe.
Isn't it ideal for like bigger material then, or kind of, okay.
Periodic material.
Okay, repeat it.
And there is another thing that the atomic functions do have cusps. They have discontinuity at zero, which mathematicians hate, and regular people hate as well. So there is a trick of replacing absolute value to absolute value square, which looks a little crazy, right? But it gives wonderful results. It's a very big approximation, and hopefully I count on Ben on enlightening us more on Tuesday. But this is a main idea why the Gaussian software is called Gaussian, right? So exponential of absolute value square is Gaussian function. So it's Gaussian because of approximation to atomic functions. And in previous years, I scratched a couple of images. I don't know.
Well, there's the curve.
Huh?
No, there's the curve that you're showing there.
Yeah. So cusp, and the plane wave, it just oscillates. But you know, Fourier transform enables to represent any function as a superposition of oscillations. And if like s orbital in point r1, s orbital in point r2, it's one-dimensional projection, right? And p orbital in point r2. So the quick decrease of the function as we depart from the center of atom is the same for these two functions. Of course, we need to put right coefficients in front. And of course, it will diverge in the central area. So this Gaussian function will not reproduce the cast. And it will diverge in the infinity area. But in the range where chemical bonding occurs, one can, with using right coefficients, one can approximately represent atomic functions with Gaussian functions. And then several mathematical operations, both analytically, if you would live like 70 years ago, or computational, get much, much quicker. Okay. So, there is a lot of redundant information. So you will not see anything new on this slide. So we are trying to put back the concept mean field, background charge, antisymmetry. We are going to replace Hamiltonian with Fock operator. That is, in format, it's like one electron operator, but in essence, it includes traces of multi-electron interaction. There will be also reflection of the fact that there is independent sets of basis functions placed at different atoms, and we will express everything in basis functions. Good. Okay. So you have seen Fock operator when we had this reminder R session. Recall? Refreshment?
Review.
Review.
Refreshment. Okay.
Yeah, refreshment session. You have seen it in explicit, almost explicit form, and here everything is encrypted. But T is kinetic energy of electron, right? It's gradient square, derivative over position squared. Nuclear to electron attraction. It's a Coulombic term with minus sign because it is stabilizing, and it has difference between position of nuclei and position of electron. And then we add this term again and again for all nuclei. So if you would have only these two, it will be Hamiltonian. But since we have a term that reflects electron-electron interaction, it is Fock operator. There is a letter F. And some texts use letter J for direct for Coulomb propulsion. And we make summation of repulsion of our electron 1 from all other electrons. You make summation to the number of electrons. Right? Yes, please.
So, I'm trying to understand that what is the limitation here that we're rearranging these electrons as you described earlier in the Fock matrix? How does this kind of limit us? Because we got a good, looks like we have a good explanation of, but are we going to get to the limitations of the system?
Of these equations, we should.
Okay.
But it's not exact. It is an approximation.
Right.
And it
right.
will, if you find either solution of multi-electron function by superior methods, or you make measurements, Hartree-Fock results will always deviate.
Right, but I want to understand like what you said earlier about rearranging it according to the slide.
The slide.
Right,
So
right.
this capital F is the same capital F.
Right.
The only difference here it is in general form of operator, and here it will be in matrix form.
Mm-hmm, mm-hmm.
Okay?
Right.
So I'm only covering which terms are included there, and
Right.
introducing notations that you may see in texts if you will be curious and you open books.
Okay. Okay. Okay.
So this is positive Coulomb repulsion from all but one electrons, and this is exchange of our first electron with all but one electrons.
Right.
Which is stabilizing.
And you were saying there wasn't a distinction between the last electron and the first electron, so that's why you're able to rearrange, like you have to reconstruct it. And I was trying to understand what you were saying by that. Like, that's just how this is defined, correct? Just how this I'm just trying to understand because I got.
I'm also trying to understand. So, how I make myself in peace with all this stuff.
Okay.
I imagine that we do have a skeleton of molecule, and we ionize it completely, n times, where n is number of electrons.
Okay.
Right?
Right.
And then we start throwing all electrons back, hoping that they are taking the right orbitals and they taking the right shapes.
Okay. Okay.
And then this operator here is one electron operator. It already includes integration over positions of all except one electrons.
Okay.
Should I jump back to the slide where it is shown?
Sure.
Or
I think it's yeah. I think it makes
it
sense.
is clear?
Yeah.
Okay. So it is operator in respect only to one electron, but
Right.
it includes summation. You remember this Brian Cat expectation values
Right.
in respect to all electrons except the last one or
Okay.
the first one. It doesn't matter
Okay.
how we count them.
Okay.
Are you coming in peace?
Yes. So it's basically you're describing it. You ionized it, then you added everything back in, and then you can describe all your
How those electrons that I already returned
right.
screen the last electron, because like if I ionize everything and I just put one electron, it will be so heavily attracted, it will be just rushing to ions.
Right.
But if we fill molecule with more and more electrons, they will make like a shell,
So resettle themselves, kind
resettle, and they will protect, like cover. They will cover
so-
ions from the last electron, and the last electron will not feel ions so heavy.
So it'll shield them. It'll
Shield,
okay.
yes.
Okay.
Okay?
Perfect. All right.
So, this one is shielding against attraction to nucleus.
Okay.
And if we would not take into account antisymmetry, this shielding will be so efficient that molecules will be not stable. But due to antisymmetry, there is another stabilization factor. So this, it will be reasonable to put minus sign here for better visualization. So stabilizing, shielding, stabilizing again. And then this letter F, this operator, which acts only on electron R sub 1, acts on the unknown wave function. And if wave function is good, if it is eigenfunction of this operator, then we are happy. The solution, so there is eigenvalue problem. So the functions and energy, I did something wrong with indices. It should be I positive on both sides. Okay, so the eigenvalue problem generates a set of eigenenergies and set of eigenfunctions. And these functions are immediately used for a next step in a self-consistent, in the returning loop way. So we populate all of these orbitals with so many electrons as we have in a molecule, and they create background field that affects last electron, and then we repeat the whole procedure. Okay? So this is the idea of Hartree-Fock theory, but we are not done yet because we haven't included details about basis, which is critically important for practical computations. So you all are now certified experts in like background ideas of Hartree-Fock theory. I'm not going to tell anything new, but we still need to get to this loop and to this S capital. which doesn't immediately follow from this notation. So if you were taking background, like introductory quantum theory, you know that good solutions of Schrödinger equation, good orbitals are always orthogonal, right? Like multiplying by each other, integrating, it will give either 1 or 0, right? And it holds, it is correct, if your two orbitals that you inspect belong to the set of hydrogen atom solutions, like s and p orbitals on the same atom. There are theorems that they are orthogonal, but there are no theorems about orthogonality of atoms that belong to two different atoms, right? There, if you have atomic orbitals localized on different ions, let me put here maybe here R1 minus R capital first, here R1 minus R capital 2, something like this. If they're localized on different ions, then they can give you anything between 0 and 1. A lot of little helpful derivations in quantum theory are based here and there, like in like perturbation, time-dependent perturbation. I just cannot mention all of them. Are based on orthogonality property. But here we see failure of orthogonality due to the fact that we have different atoms, right? So it's a practical challenge. If you want to reprogram the code that will perform artifact calculations. So we need to take into account that instead of delta function, instead of orthogonality, which will be either 0 or 1, we will have this overlap matrix. Which, like, if you have 100 orbitals, it will be 100 by 100 orbitals. Same size as Fock matrix. 100 is not a big number. Maybe it's 1,000 by 1,000 or million by million for today's computation. Well, million by million is a little much, but like 10,000 by 10,000 diagonalization is trivial, right? So any place where typically in regular quantum theory we would use orthogonal property, here we will just put this S matrix, which needs to be practically computed at each iteration of Hartree-Fock theory. Right? Well, I'm lying. If it is overlaps between atomic, not molecular orbitals, then we can compute them once forever if you do not move ions. Good. And we can compute this two electron integrals with 4 indices and also use them over again. Since electrons can be, these atomic wave functions can be localized on different ions, it will be also like, it's not a matrix, it's a tensor with 4 indices. And if we are meticulous and systematic people who want to plan Hartree-Fock code for the first time, probably before we start actual calculation, we need to form this tensor of Coulombic interaction for any combination of all atomic bases on each atom.
What is a tensor?
Huh?
What is a tensor?
What is a matrix?
Well, I know what
Tell me what is a matrix. How do you define it?
Well, okay, it's a. Well,
It's a set of data records that is indexed by 2 indices, right? And tensor is more general if number of indices can be less or more than 2. Okay. Okay, so nothing new for you here, right? And we are going to include the replacement of orthogonality principle into this equation. So right now, this is in some sense abstract orbital, or orbital defined in the grid space as function of position. So it is differential orbital, right? And there is a statement. It's not like a theorem. It's just practical convenience statement. In any situation, if possible, convert your equations into matrix form if you want to solve them numerically. So how to convert this eigenstate problem into matrix form? What does it mean? So right now, unknown eigenfunction is a function of position of electron, and this is differential operator. So when we convert equation into a matrix form, we need to replace function by a vector in discrete space, and we need to replace operator by a matrix, right? For a specific basis. Good? No one objects about this idea. Okay. Now, I'm going to do two logical steps. First, remember that review that it is a molecular orbital composed as a superposition of atomic orbitals. And second, I'm going to multiply left and right part from the left by bra vector of arbitrary atomic orbital. Everyone is happy with this? Give me a little sign if you want me to speak it up in more details. Okay. So if we multiply operator by two functions from left and right and integrate, it will convert into a matrix. So in order to make it matrix, we need to multiply it by another function. Okay? And to keep the identity, we will multiply both left and right part by atomic function, and then practice orthogonality or whatever serves instead. A couple of years ago, I believe that it is main step. Maybe I'm not agreeing with it now, but at least it attracts your attention. So each of these functions is already a superposition of atomic functions. And here, I'm not writing it explicitly, but this notation assumes that it is different set of hydrogenic orbitals localized on different atoms, right? So it's all basis functions on all atoms. And here are the expansion coefficients where this nu is a cumulative index that includes everything about atomic, and I is the number of our molecular orbital. So we can replace this phi sub I by this expansion. Atomic basis functions will be not changed, so we will need to come into equation for these expansion coefficients. But by plugging in this molecular orbital expansion, we are yet in the form of continuous equation for continuous function. So, applying this procedure, correct if I can. Yes, I can. Okay. Good. So we do have this F, we do have summation over cumulative index C nu comma I chi nu of R equals eigenenergy summation nu C nu comma I chi nu, right? And now we are going to multiply by chi mu with star of R and integrate over dr. And here, to have the equivalent equation, I'm doing it on the right side as well. Chi mu star of R. So what is important that indices nu and mu, indices by atomic functions, are different. And what I just corrected from previous year, we multiply by atomic function, not molecular. Okay? So if it would be like Hartree-Fock theory for only one atom, then it would be a little easier, because wave functions will be orthogonal. We would not have this S matrix, overlap matrix. And here will be additional term. So we are going to integrate. Here, the integration. By the way, you see, C with indices is a number. Feedback? Microphone? Thank you. Well, I'm pleased to hear that someone is listening remotely. It's a little evidence. So one can, and you know that integration and summation can be swapped the order. It doesn't change anything. So we can move summation and C out of this integration, right? And here you can also put summation out of integration. Summation nu C nu I integral dr chi star mu chi without star nu equals summation nu C nu I integral dr chi star mu f chi without star nu. Okay? Now we need to discuss and define what are these two things. How would you call this integration? We discussed it like 10 minutes ago. What is this? They would be orthogonal if it would be on one atom. But since they can be, these indexes may refer to functions on different atoms, it will be overlap matrix, which may take different values between 0 and 1. So this will be S sub mu nu, overlap matrix. And this falls into definition of matrix element of an operator, right? So with this procedure, we will convert Fock operator into matrix element of Fock operator, right? So here it will be S sub mu nu, here will be F sub mu, right? Now let's jump forward. So instead of delta, it is S. We did it so much quicker, so some slides were redundant. Right? Okay, we are about here. So we are arrived to this equation, right? So there is nothing new compared to the handwritten that we were discussing a minute ago. So this one is matrix element of Fock operator, and we may just notate it as give notation F mu nu, or Brian cat notation, and this stuff will be S mu nu.
Starting to take a very familiar form.
Yes, if you look onto this chart, you arrive to Hardy-Fock equation in matrix form, right?
What happens to the V?
You mean nu?
New, I mean new, sorry.
Perfect question. So, right now, we are writing it explicitly with indices, right? But if we have matrices and vectors and their multiplications, there are two ways for notations. So one notation when you explicitly track all indices, and another way when you just agree of the size of the matrix, agree that it is square, and you symbolize maybe matrix by fat symbol, bold symbol, and vector maybe by sign of vector, and remove all indices. Okay, so in the notation that is here, you, as Mary correctly noticed, there is no index nu, and there is no index mu. So this is a matrix with two indices. This is a vector with one index. And here we do summation over nu. Nu here, nu there. So this is equivalent to what?
Okay. Well, sorry.
Simpler. Linear algebra.
Yes.
So, which rule of multiplication of what?
Matrix multiplication.
The
Row by column.
Row by
column, right? So, in this matrix, index nu corresponds to a row. And this is a vector or corresponds to different rows in the vertical matrix. Okay, and same here. Mu nu matrix is two indices. Nu is index in the vector, right?
So you're saying when we have nu here, it's in the vector, but when we write it with sub I, it's kind of like a general form, kind of.
We will come to this notation.
Okay.
So index I corresponds to, like, in energy and in eigenstates, correspond to number of molecular orbital, number of eigenstate, number of solution, right? And index nu runs over basis functions. Nothing new, just repeating, refreshing, reviewing.
All three.
If we do have Fock and overlap matrix operators in matrix form, there is no dependence on position of electrons. And even if we would work in a very rough grid space, typically the number of indices, as we go from grid space continuous distribution to basis functions, it is, in most cases, it is very strong speed up. Because you deal with analytical functions, and going to specific basis always give much, if it is possible, when needs to use specific basis. And we already agreed, it's row by column, right? When you count indices in this form. So summation the mute index that disappears, and then we just need to write down this f, s, and c as vectors. So Hartley, Fogg, and there is one person more. So Hartley and Fogg are not with us anymore, but Clemens Roothaan is still with us. He is 100 years old.
Yeah, I was looking at that date. I was like,
Yes, yes. And he was arguing with his advisor, revolted against old theories. And
he threw what through a window? He threw his thesis.
and he got insight about the equations that we are going to cover while sitting in the Chicago Opera. So, if you want to go along his path, you probably should go to Chicago Opera as a part of his
I
path.
don't know about throwing stuff out the window, but
So, slowly but surely going to notation without new. So, for eigenvector number 1, I equals 1. There will be I equals 1, and then expansion over basis function first, second, third, like SPD on the first atom, SPD on the second atom, long vector. And we can call it like C with vector, without any indices. Same for operators. So matrix element 1, 1, 1, 2, it's matrix element of contraction continuous operator between atomic orbital 1 and atomic orbital 1. Atomic orbital 1 and atomic orbital 2. And then forming a matrix, right? And then we can just use bold font F and understand that it is a square matrix of the same dimension as matching the vector. And same for the overlaps. Like if it would be single atom, it will be ones on the main diagonal and zeros outside. But since there are more than one atoms, there will be some non-zero of diagonal elements. So now we reformulate this Hartley-Fogg Roothaan equation in the matrix form. From Fogg to Roothaan. So Fogg matrix, unknown vector of expansion coefficients, unknown eigenvalue, the known matrix of overlaps, and then again this unknown vectors. So it comes closer to what you used to see in linear algebra. And it is an equation that, like, if you would live at the time when these codes were created, you probably would encode solution of the eigenvalue problem. But if you need to do it today, and if if you have practice in some programming, we would use just subroutines. Like some, MATLAB, there is a EIG procedure for diagonalizing things. In if you are doing Fortran, there is a LAPAC set of subroutines that you just call to solve eigenvalue problems. But it is style. It is style of mathematical applied math problems that is easy to solve, right? Standard to solve. What else? Let me write something. Let's simplify it a little bit more. So what if we subtract left from right? F11 minus E S11 F12 minus E S12 and so forth. F21 minus E S21 F21 minus E S21 and so forth. multiply by C1, I, C2, I, and so forth. What it will be equal to? So we just subtract, move the right part to the left, right? Put minus sign here. And then instead of two matrices multiplied by vector, it will be just one matrix. Equals what? Equals what? I've got at least one correct answer.
0?
Yes. So it is how typically the equations of linear algebra are formulated. And now we are coming to what is seen here. So the eigenvalue problems. So fog, expansion coefficient, unknown energy, overlap, expansion coefficients. Subtract from left, subtract right. So F minus ES. And then if, as you recall from your linear algebra, in order to solve this equation, you need to set determinant to 0, then convert matrix into set of polynomial equations and find roots, right? Well, if it is solved by computer, there are different algorithms, but if we would try to pretend that if you wouldn't have computers and we need to solve quadratic equation, we would do so, right? So energy will be unknown variable, and it will be polynomial equation for energies, and it will be like polynomial, like how many basis states. Like if there are 100 basis states, there will be polynomial of order 100, and then the one can draw a function that would cross axis will be equal 0 100 times crossing it, and it will be roots of equation, right? You recall it. All of us were solving at least for 2 by 2 matrices.
Yes.
And as a solution, one gets set of eigen energies. And if one plug them one by one into this equation, one would solve linear linear equation for the expansion coefficients, right? So one would get set of energies of molecular orbitals, the ones that you are getting in Gaussian, list of occupied and unoccupied orbitals. They're coming from here. So you count how many electrons, and then the one that corresponds to number of electrons will be HOMO, and the one that corresponds to number of electrons plus 1 will be LUMO, right? And the expansion, this solution for C, when you type cube gen, they are multiplied with atomic wave function and generate spatial distribution of molecular orbitals. So these C coefficients are giving us molecular orbitals, and energies give us HOMOs, LUMOs, and all energies of orbitals, right? And we can also use concept of density of states to reproduce them. Okay? Make sense? So, but the pure quantum mechanics without approximations is linear. Everything is a linear set of equations that one can diagonalize. But here is a substantially non-linear problem. If one would try to solve it analytical, then you see the background potential that acts on last electron depends on the state that this electron is taken. So they are not independent. And if one would try to solve it by pen and paper, which is a pain, and typically no one does it, it will roll into like set of equations with different order of corrections. Instead, one can just practice a procedure that if the background field that determines interaction with electrons agrees with shape of orbitals, then going through the cycle, reformulating Fock matrix, diagonalizing, finding total energy, will give you the same orbitals, the same energies, the same total energy, again and again. And if we are starting far from solution, this procedure is expected to bring us closer and closer to solution due to variational principle. Right? So it is a magnificent that we just repeat it, and at each step we will approach closer and closer to solution. But again, it is a applied math way to solve nonlinear problem. And of course, it will never be absolutely correct. It's just art of what is possible rather than science of what is needed, in some sense. So, if there is you already know through Slater determinant, matrix elements, how to find total energy. So if you have molecular orbitals, one can form Slater determinant and find total energies, including all electron-electron interactions. And then one is getting total energy at each step. If it saturates and come to asymptotically approaches some specific value, then one stops the cycle and gives normal termination of Gaussian. If they are diverging, one is using orbitals computed at the step, reformulate Fock matrix, which includes background field acting on the favorite electron, and solves Fock matrix once again. I think we're done. In record time, 1 hour and 9 minutes. Thank you. I will stay here and answer any questions, but formal part of lecture is done. Have a pleasant Friday and nice weekend. And I will try to answer emails as quick as I can, especially for the questions related to your presentations on Tuesday.
I actually do have a question, so let me just bring it up to you.
Those who want to ask questions remotely, you can switch on the microphones or email those who are in class or directly to me.
Okay, I had a question on my structure.
Okay, I'll probably put us off record.
Okay.